Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to define our equilibrium expressions for our weak acids and bases and also for water. Now we're not doing any calculations yet because we first have to know how to write these expressions before we can do calculations. So let's see what these equations are. Let's start with a concrete example. So if we write the equilibrium expression for hydrofluoric acid, which is a weak acid, we get this chemical equation. Now let's just write the equilibrium expression first for this equation. Whenever we're doing an equilibrium expression, of course, it's the concentration of the products divided by the concentration of the reactants. There is our equilibrium expression. Now, when we're talking about an acid, we assume that the concentration of water stays constant. So this becomes not a variable, but a constant, and it's generally about 55.1 molar. So we are actually going to fold this constant into our equilibrium constant. Now bringing that concentration of water over to the left side of the equation turns this KEQ into something very specific. It now becomes a Ka. Of course, we call it Ka because we're talking about an acid. Now, this is specifically for hydrofluoric acid, but let's see what happens when we have a generic acid. So here is an equilibrium equation for a generic acid, Ha. This proton is the one it's going to donate. A minus is its conjugate base. We can write the equilibrium expression for this. But of course, we're going to assume that the concentration of water is constant. We are going to turn this into a Ka. And this is our Ka for a generic monoprotic acid. You will see this quite often. Now, of course, we can do equilibrium expressions not just for acids, but also for bases. So again, let's start with a very specific base. Let's start with ammonia. Here is the chemical equation for ammonia. Let's just write an equilibrium expression. Just like with the acid, when we are in aqueous solution, we are going to assume that the concentration of water is constant at about 55.5 molar. So we are going to fold this into our KEQ. Our KEQ times our concentration of water becomes Kb, since we're talking about a base. Of course, just like we did for the acids, it's very helpful to get a generic equation for all bases. So here is our chemical equation for bases acting in water, and let's get a Kb for this. Of course, to go from our KEQ to our Kb, we take our concentration of water over to the left-hand side. And there is our generic expression for a base. Of course, because we are working in aqueous solutions, we do need to talk about water. So here is the equation for the autoionization of water. Again, if you need any review on the autoionization of water, you can check out my video on that. Let's write an equilibrium expression for it. Now, even though we have the concentration of water twice in the denominator, it is still a constant. So let's fold this into our KEQ, and we will turn this into a KW expression. Now let's see what happens when we have an equilibrium expression for a weak acid and also its conjugate base. So first, here again is the equilibrium expression for a weak acid HA. But right next to it, I have written the equilibrium expression for the reverse reaction for what happens to A minus. Let's get KAs and KBs for these two equations. Now don't forget, my Ka includes my concentration of water, so it is not in my expression on the right-hand side. And for my Kb, okay, now what happens if we multiply Ka times Kb? Okay, my expression for Ka multiplied by Kb when we do this, notice that your concentration of A minus cancels, your concentration of HA cancels, and we are left with recognize this expression? We just did it. This is Kw. So therefore, if we multiply Ka and Kb for a conjugate acid-base pair, we will get Kw. Now I do want to be really clear that this is for a conjugate pair. So if I were to multiply the Ka for hydrofluoric acid times the Kb for ammonia, I would not get Kw. This must be for a conjugate pair. This is very helpful because usually when you look up equilibrium constants in a table, you will only get Kas. However, you can convert them to Kbs through this expression. There is one other equation that I just want to mention, and that is percent ionization. So once we start doing calculations and we start getting concentrations for our hydronium ion, for our weak acids and our weak bases, we can calculate how much of a weak acid or a weak base actually ionizes using these equations. I know we went through a lot of transformations and permutations in all of our equilibrium expressions, but being able to work with them algebraically before we start putting values in is actually going to be a huge help when you start using them to calculate things like pH. I hope you found this video helpful, and thanks so much for watching.